The morning of October 14th, 1944, near the village of Schmidt in the Hürtgen Forest, Obergefreiter Wilhelm Brenner crouched behind the splintered remains of what had been a church wall, his hands trembling as he tried to reload the last shell into his unit's 15-centimeter schwere Feldhaubitze 18. Around him, the methodical thunder of American artillery had been falling for 3 straight hours, but this wasn't the slow, deliberate barrage they'd learned to expect from British guns or the sporadic fury of Soviet artillery. This was something different. Every 8 seconds, like clockwork, another American shell screamed overhead. Every 8 seconds. The mathematical precision of it was what unnerved Brenner most. His crew had spent the morning counting, timing, calculating. The Americans weren't just throwing more shells, they were throwing them faster than any artillery doctrine said was possible. What Brenner was experiencing was the culmination of a revolution in artillery design that had begun years earlier in the workshops of Rock Island Arsenal and the testing grounds of Aberdeen Proving Ground. The American M114 howitzer, originally designated the 155mm howitzer M1, could sustain a rate of fire of 4 rounds per minute, translating to 1 shell every 15 seconds during sustained fire, and achieving bursts of 6 rounds per minute during intense bombardments, putting shells downrange every 10 seconds. But the German experience that morning suggested something even more remarkable was happening. When multiple American batteries coordinated their fire using the revolutionary time-on-target technique, shells from different positions fired at precisely calculated intervals would arrive simultaneously, creating the illusion of impossibly rapid fire from a single source. What felt like one gun firing every 8 seconds was actually a carefully orchestrated symphony of destruction. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The foundations of this artillery revolution had been laid a decade earlier in the dusty training grounds of Fort Sill, Oklahoma. Major Carlos Brewer, director of the gunnery department in the late 1920s and early 1930s, introduced new fire direction techniques so fire support would be more responsive. Major Orlando Ward, the next department director, developed the Fire Direction Center to centralize command and control and facilitate massing fire. These innovations represented a fundamental shift in artillery philosophy. Traditional European methods treated each battery as an independent unit, firing independently controlled missions. The American system created a centralized brain that could coordinate multiple batteries as a single weapon system. During World War II, to best use new, long-range guns and better response times, the Field Artillery School championed the use of air observation to control artillery fires. The context matters here. By October 1944, German artillery was fighting a losing battle against American innovations that fundamentally challenged everything the Wehrmacht had believed about indirect fire. The German SFH-18, their standard divisional howitzer, could manage a maximum rate of 4 rounds per minute under optimal conditions, but battlefield reality was far harsher. Crew fatigue, ammunition shortages, and constant Allied air harassment meant German batteries were lucky to sustain 2 rounds per minute. The statistical disparity was staggering when you examined actual battlefield performance. A typical German artillery battalion in October 1944 consisted of 12 SFH-18 howitzers. Under ideal conditions, firing at maximum theoretical rate, they could deliver 48 rounds per minute. But ideal conditions never existed. Ammunition rationing meant batteries were limited to 10 to 20 rounds per gun per day. Crew replacements often had minimal training. Allied air superiority meant daylight firing invited immediate retaliation. An American artillery battalion with 18 M114 howitzers could theoretically deliver 72 rounds per minute at sustained rate, or 108 rounds per minute during burst fire. More importantly, American logistics could sustain this pace. By late 1944, ammunition shortages meant German artillery could only fire about 10% of what British artillery was firing, despite having comparable numbers of guns. The Americans had approached the same tactical problem from an entirely different philosophical direction. Where German doctrine emphasized precision and methodical fire control, American artillery training prioritized speed and volume of fire. The M114's semi-automatic breech mechanism opened automatically after firing and ejected the spent cartridge case, allowing immediate loading of the next round without manual breech operation. This single mechanical innovation cut reload time nearly in half compared to the German system. The design philosophy behind these weapons revealed two nations that had learned opposite lessons from the Great War. Germany emerged from 1918 convinced that artillery had been too crude, too wasteful. The solution, in their view, was precision. The SFH-18 used a horizontally sliding wedge breech block that was manually operated, robust and precise, but also slow. Every element of the weapon assumed that well-trained crews would make the difference through careful, methodical operation. The German approach reflected traditional continental military thinking. Artillery was a scientific instrument requiring master craftsmen to operate effectively. The SFH-18's sighting system was superb, featuring precision optics that allowed accurate engagement at maximum range. The ammunition was manufactured to exacting standards, ensuring consistent ballistic performance. The crew drill emphasized doing everything correctly rather than doing everything quickly. This philosophy worked brilliantly during the campaigns of 1939 through 1941, when German artillery supported rapid mechanized advances against enemies who lacked effective counter-battery capability. But by 1943, the operational environment had changed completely. Static fronts, attritional warfare, and Allied air superiority meant German guns needed to fire quickly, then displace before enemy counter-battery arrived. American engineers had studied the same problem and reached a radically different conclusion. The M114 program began in 1939, when the US Army realized its existing 155mm guns were obsolete. The design team incorporated lessons from both French and British designs, then built a weapon optimized for mass production and ease of use. The Rock Island Arsenal design team faced a specific challenge: create a weapon that could be operated effectively by rapidly trained crews rather than artillery specialists. This drove every design decision. The carriage had to be simple enough for maintenance by field mechanics. The firing drill had to be standardized so crew members could be replaced without retraining entire teams. The mechanical systems had to function reliably under field conditions without requiring constant adjustment. The carriage design alone illustrated this philosophical divide. The M114 used a split trail design with two separate trails that spread apart, giving the gun a much wider traverse arc without repositioning. A German SFH-18 crew needed to physically move their entire gun to engage targets more than 5 degrees from their initial aim point. American crews could traverse 15 degrees in either direction without breaking their firing rhythm. This traverse advantage translated directly to tactical flexibility. During fire missions, targets often shifted as enemy forces maneuvered or as forward observers identified new priorities. The M114 could engage multiple targets in sequence without losing firing tempo. The SFH-18 required crew members to manhandle the trails into new positions, a process that could take several minutes and left the crew exposed. The recoil systems told a similar story of competing design philosophies. The M114's hydraulic recoil system used hydraulic buffers with compressed air recuperators. When the gun fired, hydraulic fluid absorbed the recoil energy smoothly, and compressed air pushed the barrel back into battery automatically. The system was faster, more consistent, and required less maintenance than spring mechanisms. German crews had to wait for spring-loaded mechanisms to cycle, adding precious seconds to every shot. Worse, spring systems degraded over time and required constant adjustment to maintain proper timing. The hydraulic system automatically compensated for wear and temperature variations, maintaining consistent performance across thousands of rounds. But the real breakthrough was the semi-automatic breech mechanism. The M114 used an interrupted screw design with a semi-automatic feature. After firing, the breech opened automatically and ejected the spent cartridge case. The loader could immediately insert the next round without waiting for manual breech operation. This wasn't revolutionary technology. The French had used similar systems in World War I, but American engineers had refined it to the point of battlefield reliability. The breach mechanism represented perhaps the most fundamental difference between German and American artillery philosophy. German engineers viewed the breach as a precision instrument requiring careful operation. The horizontal sliding wedge system provided excellent gas sealing and could withstand tremendous pressure, but it demanded skilled operation and regular maintenance. American engineers approached the breach as an industrial component that needed to function reliably, regardless of operator skill level. The interrupted screw mechanism was inherently self-timing. When properly loaded, the breech would close correctly. When fired, it would open and eject automatically. Crew training focused on loading rhythm rather than mechanical operation. The ammunition handling systems reflected the same philosophical divide. American bagged powder charges were lighter and easier to maneuver than German brass cartridge cases. The M114 used separate loading ammunition, a lessive, projectile and powder bag loaded separately. This system allowed rapid adjustment of propellant charges for different ranges without switching entire rounds. German separate loading ammunition worked similarly in principle, but the implementation revealed different priorities. German powder charges were manufactured to precise specifications for maximum accuracy. American charges were designed for speed and consistency of handling. German loaders had to carefully select the correct charge for each shot. American loaders could grab standardized charges that worked effectively across most firing situations. The crew training methods illustrated these competing approaches most clearly. German artillery schools trained gunners to operate their weapons perfectly. Students learned to calculate firing data manually, adjust for weather conditions precisely, and maintain equipment to exacting standards. The emphasis was on technical mastery and individual skill. American artillery training emphasized standardization and speed. Fort Sill instructors drilled their students until 4 rounds per minute became muscle memory, not heroic effort. Students learned to operate within a system rather than master individual components. The Fire Direction Center calculated most variables automatically. Crew members focused on executing standardized procedures rapidly and repeatedly. This systematic approach extended to every aspect of artillery operations. German fire missions required detailed planning and careful execution. Forward observers calculated coordinates manually, transmitted detailed instructions, and adjusted fire through careful observation of shot results. The process was methodical, accurate, and slow. American fire missions emphasized speed of response over perfect accuracy. Forward observers could call for fire from any artillery unit within range, not just their assigned batteries. When these observers requested fire missions, pre-computed settings allowed batteries to begin shooting immediately without ranging shots. The Fire Direction Center system revolutionized coordination between observation and execution. Instead of individual batteries operating independently, multiple batteries could be controlled as a single weapon system. A typical center could coordinate 72 guns from 3 battalions in massive time on target. Missions. The process that took German or Soviet batteries 10 to 15 minutes could be completed by Americans in under 2 minutes. The first M114 howitzers fell into German hands during the North Africa campaign, though initially in damaged condition. Operation Torch. The Allied landings in Morocco and Algeria in November 1942 introduced American artillery doctrine to the Mediterranean theater. By early 1943, as US forces pushed through Tunisia, German technical intelligence teams were recovering abandoned equipment from battlefield losses. The initial captures provided incomplete intelligence. Battle damage obscured many design features, and German engineers couldn't conduct comprehensive testing without intact weapons and ammunition. But even partial examination revealed troubling capabilities. The split trail carriage was obviously superior for rapid target engagement. The hydraulic recoil system appeared more sophisticated than German spring mechanisms. More complete intelligence came from the Sicily invasion in July 1943. The chaotic fighting around the beachheads meant both sides lost and recovered equipment multiple times. At least 2 M114 howitzers were abandoned during the initial beachhead crisis, then recovered by German forces before the Allies could destroy them. These guns came with something even more valuable than the hardware itself: American ammunition and technical manuals. The Wehrmacht had a well-established system for evaluating captured weapons. Every major front sent technical intelligence teams to recover enemy equipment. Anything interesting went back to Germany, usually to proving grounds at Hillersleben near Magdeburg or Kummersdorf south of Berlin. These facilities had been testing artillery since Imperial German Army days and had evaluated Soviet, British, and French weapons throughout the war. The evaluation process was systematic and thorough. Static inspection came first, examining construction methods, materials, and mechanical systems. Engineers measured dimensions, analyzed metallurgy, and documented every component. Then came live fire testing, comparing performance against German weapons under identical conditions. Finally came tactical evaluation, assessing how the weapon would perform in actual combat scenarios. When the first complete M114 arrived at Hillersleben in mid-1943, initial reports focused on obvious features: the split trail carriage, hydraulic recoil system, and semi-automatic breech. German engineers recognized immediately that this was a modern, well-designed weapon. The construction quality was excellent, the materials were first-rate, and the engineering was sophisticated without being overly complex. But the real revelation came during live fire testing. The test protocols at Hillersleben reflected combat reality: fire as fast as possible for 5 minutes, then maintain steady fire for 20 minutes, then measure crew recovery time. The M114 crews consistently hit 4 rounds per minute during sustained phases, occasionally spiking to 5 or 6 rounds during initial bursts. More importantly, the weapon itself showed no mechanical stress. The hydraulic recoil system maintained consistent performance across all test firings. The breech mechanism didn't require additional cleaning or cooling after rapid-fire sequences. The gun could theoretically maintain this pace as long as ammunition lasted. The German SFH-18 crews firing the same test profile peaked at 3 rounds per minute during initial bursts, but dropped to 2 rounds per minute during sustained fire. Not because the crews were inferior, these were veteran gunners selected for their expertise, but because the weapon demanded more physical effort and more time for each operation. The technical reports documented this finding with characteristic German thoroughness. Engineers measured breech operation, timing, recoil cycle, duration, and crew loading sequences. They compared the M114's performance against the SFH-18, firing under identical conditions, with similarly experienced crews. The conclusion was unavoidable. The American weapon was sustaining twice the rate of fire of its German equivalent because of design features that reduced crew workload rather than increasing crew skill requirements. German engineers also evaluated what they didn't yet call ergonomic aspects. The M114's crew positions minimized movement conflicts. The loader and assistant loader worked on opposite sides of the breech, never interfering with each other. The powder handler stood clear of the loading sequence. Every crew member had a clearly defined role that didn't conflict with others' movements. The German SFH-18, by contrast, required more choreographed teamwork. The breech operator had to manually close and lock the wedge block, then clear the area before the gun commander called fire. The loader and assistant had to work in sequence rather than parallel. Every extra second of coordination multiplied across crew fatigue and stress conditions. The ammunition handling tests revealed another systematic advantage. American bagged powder charges were lighter and easier to maneuver. The M114 used separate loading ammunition with projectile and powder bag loaded separately. This system allowed crews to adjust propellant charges for different ranges without switching entire rounds. German separate loading ammunition worked similarly in principle, but American bags were designed for speed. They stacked efficiently, ignited consistently, and produced less residue buildup in the chamber. The test reports noted that after 100 rounds, the M114's breech required only basic cleaning, while the SFH-18 needed more intensive maintenance to maintain safe operation. Additional M114s had been captured on the Eastern Front, where Lend-Lease deliveries meant Soviet forces were also using American artillery. The Locke, Germans recovered several more guns during their fighting withdrawals through Ukraine and Belarus. Each captured weapon went through the same evaluation process, and each one confirmed the earlier findings. By early 1944, the German ordnance establishment had a clear picture of what they were facing. American artillery doctrine wasn't just about having more guns. It was about having guns specifically designed to exploit rate-of-fire advantages in modern mobile warfare. The detailed test reports from Hillesleben painted a technical picture that went beyond simple round counts. The tactical implications of this rate-of-fire gap became clearest when examining how each side used artillery in combat. American doctrine by 1943 revolved around time-on-target missions. Multiple batteries fired at precisely calculated times, so all shells arrived simultaneously. A properly executed time-on-target mission could drop 200 rounds on a single objective in, say, 30 seconds. The shock effect was overwhelming. German infantry reported that TOT strikes felt like the ground itself was exploding. There was no warning crescendo, no time to take cover. One moment you're in position, the next moment everything within 100 meters is erupting. The psychological impact matched the physical destruction. But TOT missions only worked if your guns could fire rapidly enough to deliver the required volume before the opportunity window closed. American batteries could shift fire, calculate firing data, and start putting rounds downrange in under 3 minutes. The first salvo might not be perfectly accurate, but it didn't need to be. Volume compensated for precision. German artillery doctrine still operated on World War I principles of methodical barrage fire. A typical German fire mission started with ranging shots. Forward observers identified a target, calculated coordinates, and called for registration rounds. Single shots were adjusted until they bracketed the target. Only after registration did the fire for effect phase begin. This approach maximized accuracy and ammunition efficiency. It minimized waste. It also gave enemy troops time to recognize they were being targeted and seek cover. By the time German shells were falling in effective concentration, experienced Allied infantry had already dispersed or gone to ground. The Normandy campaign demonstrated this dynamic at operational scale. American artillery battalions regularly executed mass fire missions with 12 or more batteries participating. German defenders reported the effect as continuous thunder, a rolling barrage that never seemed to pause. Counter-battery fire illustrated the gap most dramatically. When Allied forward observers spotted German gun positions, they called for immediate suppression. American batteries could deliver suppressive fire continuously because their rapid fire rate meant suppression was uninterrupted. German crews had two choices: stay and take casualties or displace immediately and cease supporting their own infantry. When the situation reversed and German observers spotted Allied batteries, the response sequence was slower. Calculate data, shift guns if needed, begin registration. But by the time German ranging shots started landing, American batteries had often already displaced. The faster-firing guns could deliver their mission and move before counter-battery arrived. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. One particularly revealing incident occurred during the fighting near Saint-Lô in July 1944. Hauptmann Friedrich Kellner of the 352nd Infantry Division was captured with several intact fire control documents that detailed German attempts to counter American artillery. His unit had calculated that they were being outfired 4-1, and that was being generous. Some American fire missions delivered 10 times more shells in the same time period. Kellner's documents revealed the German dilemma in stark mathematical terms. His battalion's 3 batteries of 4 guns each could theoretically deliver 24 rounds per minute under optimal conditions. But optimal conditions never existed. Ammunition rationing limited them to sustained rates of 8 to 10 rounds per minute for the entire battalion. The American battalions they faced typically had 18 guns that could sustain 72 rounds per minute. During burst fire phases, American rates approached 120 rounds per minute. The mathematics were overwhelming, but the tactical implications were even worse. German fire missions required careful planning and coordination. Target identification, coordinate calculation, charge selection, and range adjustment took time. By the time German shells were falling effectively, American infantry had usually completed their immediate objectives and moved to new positions. American fire missions emphasized immediate response over perfect accuracy. Forward observers with frontline units could call fire from any available battery. Pre-computed firing data meant shells could be falling within minutes of target identification. Even if the first rounds missed, the rapid follow-up guaranteed target suppression. The Eastern Front showed similar patterns once Soviet artillery began receiving American weapons through Lend-Lease. The Red Army received hundreds of M114 howitzers, and Soviet artillery doctrine evolved to emphasize mass fires and rapid response. German artillery on the Eastern Front, already struggling with ammunition shortages and crew casualties, found themselves facing the same overwhelming volume they'd experienced in the West. Soviet commanders quickly grasped the tactical advantages of rapid-fire artillery. The traditional Russian approach had emphasized massive concentrations of guns, firing relatively slowly. The introduction of American weapons allowed smaller numbers of guns to achieve similar suppressive effects through higher rates of fire. By late 1944, Wehrmacht artillery effectiveness had degraded not because German gunners lacked skill, but because their weapons and doctrine couldn't compete with enemies who'd optimized for speed and volume. The methodical approach that seemed professional and scientific in the 1930s had become predictable and slow. The German response to documented American superiority followed predictable patterns: engineering studies, modification proposals, and retraining programs. The Wehrmacht commissioned several urgent projects in late 1943 aimed at improving the SFH-18's rate of fire. One proposal involved retrofitting semi-automatic breech mechanisms to existing guns. Engineers at Rheinmetall developed a prototype modification that replaced the manual wedge block with an interrupted screw design similar to the M114's. The prototype worked in testing, increasing rate of fire to roughly 3 rounds per minute, but implementation faced insurmountable obstacles. Retrofitting thousands of guns already deployed across multiple fronts required factory time, skilled labor, and materials that simply didn't exist. In 1944, Germany was struggling to produce enough basic ammunition and spare parts. Breech modifications for marginal improvements couldn't compete for resources against more critical needs like anti-tank guns and aircraft production. Another approach focused on crew training reforms. The artillery school at Jüterbog issued new training directives in early 1944, emphasizing speed drills. Some units reported modest improvements. Veteran crews managed to sustain 2.5 rounds per minute under ideal conditions, but training couldn't overcome mechanical limitations. The SFH-18's recoil system still needed 4 seconds to return to battery. The manual breech still required physical operation. The box trail still limited traverse. You couldn't train your way past physics. The training reforms also arrived too late to matter strategically. By mid-1944, German artillery units were being filled with undertrained replacements. Some German commanders attempted tactical adaptations to compensate for rate of fire disadvantages. They experimented with concentrated battery deployments, putting more guns in smaller areas to achieve higher local shell density, even with slower individual gun rates. This approach sometimes worked in defensive situations where German artillery could pre-register targets and fire from prepared positions. But concentration also made batteries more vulnerable to Allied airstrikes and counter-battery fire. A single well-placed Allied fire mission could knock out multiple German guns that were clustered too tightly. Other units tried rapid displacement tactics. Fire a quick mission, then move immediately before counter-battery arrived. This worked better, but it still couldn't match the volume American batteries delivered. A German battery firing 10 rounds, then displacing, couldn't suppress targets as effectively as an American battery firing 30 rounds from the same position in the same time period. The German armaments industry did manage to field one new weapon that addressed the rate of fire problem: the 15-centimeter Cannoni 18 in new carriage, basically an SFH-18 barrel mounted on a newer carriage with improved traverse. Production began in late 1944, but only a few hundred were manufactured before the war ended. Even this improved model couldn't match Allied rates of fire because it still used the same basic breech system and recoil mechanism. The new carriage helped with rapid target switching, but it didn't solve the fundamental issue. Germany simply didn't have time or resources to design and field a completely new howitzer optimized for rapid fire. The V-weapon programs were absorbing enormous resources that might otherwise have gone to conventional artillery development. But even without V-weapons, the strategic situation by 1944 made major artillery programs impractical. Material shortages, bombed factories, and disrupted transportation made producing existing weapons difficult enough. By the final months of the war, German artillery had effectively conceded the rate of fire battle. Ammunition shortages meant that even theoretical fire rates became irrelevant. Units were rationed to 10 or 20 rounds per gun per day. At that point, whether your gun could fire 2 rounds per minute or 6 didn't matter because you didn't have shells to sustain either rate. The broader implications extended far beyond tactical considerations. The rate of fire gap represented a fundamental difference in industrial philosophy. German weapons design emphasized individual excellence, 12 precision, engineering, superior optics, meticulous quality control. Each weapon was crafted to perform perfectly under ideal conditions with skilled operators. American weapons design emphasized systematic efficiency, standardized production, simplified operation, optimized logistics. The maximum rate of fire of 4 rounds per minute sustained wasn't achieved through superior individual skill, but through mechanical design that reduced crew workload. The weapon enabled the crew rather than demanding exceptional performance from them. This philosophical divide manifested in every aspect of artillery operations. German crews were trained to be artillery specialists who could coax maximum performance from precision instruments. American crews were trained to be system operators who could execute standardized procedures rapidly and repeatedly. The psychological impact on German troops was profound. Veterans who had faced Soviet artillery and British bombardments consistently reported that American fire was different, not necessarily more accurate shot for shot, but relentless in its intensity and impossible to predict. Lieutenant Hans Gutmann of the 2nd Panzer Division wrote in his diary during the Normandy fighting, "The Americans have turned artillery into mathematics. Every time we attempt to move, their shells arrive before we can complete the maneuver. It is not that their individual shots are more deadly than ours, but that they never stop firing." This systematic approach to artillery represented something new in warfare, the application of industrial mass production principles to battlefield tactics. The M114 wasn't just a better gun, it was a component in an integrated system that included training, logistics, fire control, and tactical doctrine. The lessons from captured M114 testing didn't vanish with Germany's defeat in May 1945. If anything, Allied artillery performance in World War II became the foundational case study for post-war artillery doctrine worldwide. NATO standardization agreements in the 1950s explicitly adopted rapid sustained fire as a core requirement for all member nation artillery. The benchmark rate for 155mm howitzers became 4 rounds per minute sustained. This wasn't arbitrary. It was the M114 standard validated by 4 years of combat across every theatre. Nations joining NATO had to meet this standard or replace their artillery entirely. The message was clear. Precision without speed was obsolete. Volume of fire had become the defining characteristic of effective artillery. West Germany's rearmament presented a particularly interesting case. When the Bundeswehr formed in 1955, former Wehrmacht officers were involved in planning, and they remembered the rate of fire gap all too well. The Bundeswehr didn't resurrect the SFH-18 or attempt to rehabilitate German World War II artillery doctrine. Instead, they adopted American weapons and training methods wholesale. Initial Bundeswehr artillery battalions, equipped with the M114 howitzer, purchased directly from US surplus stocks. German crews trained at American artillery schools learned American fire direction procedures and practiced American mass fire techniques. The very weapon that had humiliated Wehrmacht artillery officers in 1944 became the foundation of German Cold War artillery. By the 1960s, when Germany began developing indigenous weapons like the FH-70 howitzer, the design requirements explicitly included sustained fire rates, matching NATO standards. The Soviet Union drew similar conclusions from studying captured German reports and their own experience with Lend-Lease artillery. Post-war Soviet howitzer development prioritized rate of fire alongside range and shell weight. Soviet artillery doctrine evolved to emphasize overwhelming firepower, delivered rapidly, the same principle American gunners had demonstrated in 1944 and 1945. The M114 itself served far longer than anyone in 1942 expected. U.S. Army artillery battalions used it as their primary medium howitzer through the Korean War, where its rapid fire capability proved decisive in defensive battles. The gun saw extensive service in Vietnam and remained in U.S. Army service until the 1990s. Total production exceeded 10,000 weapons. For a design that began as a stopgap measure in 1939, that's a remarkable service record. Many nations still use it today. But the M114's real legacy isn't the weapon itself, it's the doctrine it enabled and the standard it set. Modern artillery has moved beyond towed howitzers to self-propelled systems with automated loading, digital fire control, and even more impressive rates of fire. The American M109 Paladin can fire 4 rounds in under a minute, then displace before counter-battery arrives. The German PZH-2000 can fire 10 rounds in less than 60 seconds using burst fire modes. These capabilities trace directly back to the World War II revelation that rate of fire matters more than incremental improvements in accuracy or range. That German test officer standing at Hillersleben in 1944, watching a captured American howitzer outpace everything German artillery could field, was witnessing the future. The artillery piece that shocked Wehrmacht observers with its 4 rounds per minute became the baseline for everything that followed. A mechanical demonstration that sometimes the side that shoots faster wins, regardless of whose engineering tradition runs deeper or whose individual craftsmanship is superior. Back in that shattered church near Schmidt, Obergefreiter Brenner survived the October bombardment, though his unit was effectively destroyed as a fighting force. In his post-war memoir, he wrote, "We had spent years perfecting our gunnery, believing that precision was paramount. The Americans taught us that in modern war, the gunner who fires 4 times while you fire once will win, even if your single shot is perfect. Mathematics defeated craftsmanship. The shells that fell every 8 seconds that morning weren't just high explosive and steel. They were the physical manifestation of an industrial democracy that had transformed warfare itself, turning artillery from a craftsman's art into a systematic science where victory belonged to whoever could deliver the most effective firepower in the shortest time. The age of artisanal warfare was ending, replaced by the mathematics of mass production applied to the science of destruction." Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.